All right, so welcome back. What we talked about just before the break was, of course, the organization of the data, but we didn't ever actually get to use it. We need to implement operations on it, and that's what we're going to talk about now. The most basic concept here is that of a task. This connects the control and model that we talked about before to the actual parallelism. Then that means that tasks are the thing that determine where the data is going to be stored and how it's going to be operated on. And so we will actually take a bit of time just talking about how we declare a task. There's more of that than there is about how we implement it. So just to review, we saw this diagram before. We're just showing here that we have finished talking about the driver at the top, and we are now talking about the actual tasks and eventually kernels at the bottom. So a task is just a C++ function fundamentally, but it needs to operate on one of these distributed data structures. And that means that it actually has a very interesting way of being called. On the action side, we call the task, but we need to provide arguments that are actually names for the resources that we're going to use rather than those resources themselves. And on the task side, we will receive these via parameters that provide access to those resources. You can't construct those parameters yourself. You declare them for a task, and you issue a task launch, and FleCSI creates them for you. And they are not, in general, the same type as the argument that initializes them. It's also possible, although we're not going to have time to talk about how here, for clients to define their own task parameter and argument types to extend this mechanism. So in order to talk about providing data to a task, we have to talk about the connection between the fields and the tasks. We registered fields on specializations. This causes every instance of the associated type to have that field. It is as if we could add a member to the C++ type that is our mesh, as if we could write mesh.mass field once we have a mass field, but that's not actually valid syntax. So instead, we write mass field as a function of the mesh. And what that produces is a value called a field reference. And the only way that data is ever accessed in FleCSI is by passing that field reference to a task. So when these things are first used, FleCSI allocates memory for you, and it releases it when the associated topology is gone, since then it's impossible to make these anymore. So what does this look like? On the action side, you get the scheduler, which we saw very briefly when we were creating topologies, and you call s.execute, and you say what task you want it to launch. It actually looks a fair bit like an ordinary C++ function call, except that the task that you want to launch is provided as a template argument rather than as directly the thing being called. And then you supply things like these field references, where we have some mesh pointer and we have field 1 and field 2 defined on that. And those field references recruit the appropriate data, and then eventually the task will be launched once per color on that appropriate data. So we should go through a couple of examples of how you can declare a task and talk about the different features that are present in that declaration. So here's the first example. This task, first notice, is a function template. Function templates can be valid tasks, but it is impossible to deduce their template arguments. So we see here that we are having to supply the int for it when we launch it. This is because of the mismatch between the argument types and the parameter types that can't automatically be connected. Then you can provide arguments, arguments and then parameters of a variety of types. For instance, you can have a standard vector as a parameter type. And the restriction, though, is that they have to have the same value on every process, because even the main program is running in parallel on every process. So that means that the call to s.execute takes place on every process. And because there might not be the same number of point tasks as there are processes, it would not be meaningful to have different processes disagree about what point tasks are supposed to run. The last thing to point out here, for the same reason, because there's no direct connection between the caller and the callee, it's not very meaningful to throw an exception from a task, and so we require that they be marked no except to indicate that. Then we have another example here, and in this example we start using the actual special FleCSI types. The first of these is what's called an execution space. It specifies where the task should run. You can have CPU, which is the default if you don't have one, as well as GPU, OpenMP, or a special type accelerator. In the next module, we will talk about how to use these, and in particular what the special value accelerator means. We will also cover how it's possible to write a task that actually can be used on multiple execution spaces, but for now, that's how you pick one of them. This execution space also provides a means to ask questions about what the launch was like how big the launch was and which point task you are inside the task. And we will come back very soon to say what else you can do inside a task. But for now, we will just say that when you call this, you still need to have an argument for this parameter, but because the whole point is that you're not choosing where things run, FleCSI is doing that for you, you simply supply this fixed token called on that says we're going to run it on something. We will figure out what dynamically. And then you will notice that we have an accessor here. We use the same FleCSI field of int type or double ragged that we talked about before to register fields. Now you use them to declare the accessor parameters that you need. So you take the same type, but instead of definition, you put accessor. And the accessor is the parameter that contains pointers to the actual data when you match it with a field reference in the call. And I'm not showing it here for simplicity, but when we do the hands-on, we will also have a topology accessor that lets us get data about the shape of the mesh that we're using in a similar fashion. Then there is the special case of a mutator. A mutator, well, I should say what it isn't. An accessor, even if it has read-write privileges on a ragged field, that means it can read and write the elements, but it cannot change their number in any place. And the reason for that is that it requires additional bookkeeping and overhead to change their number, and we don't want to do that gratuitously. So if you do want to, you use something called a mutator. The mutator gives you that additional power, and so you can use mutators with any of the 3 dynamic layouts that we talked about to change how many particles there are or add and remove elements from a sparse field. Then you will have noticed that there are these markers after the accessor and mutator. These are the privileges. And they come in the 4 varieties of read and write and not read and not write. These define what you're going to do with the data, and they are used by the FleCSI runtime to determine which tasks can run in parallel and which ones use the same data and thus must be serialized. They are also used to control when ghost copies take place. So the first thing to say here is that you have to use a write-only accessor or mutator to initialize a field because there is no meaningful data to read the first time. And the other thing to say about it is what it means when you have multiple privileges, as we saw there. And that controls ghost copies, and we want to say what the exact rules for that are. If you have 1 privilege, there are no ghosts. Everything is exclusive. If you have 2 privileges, it's shared and ghost, and writes to the first necessitate ghost copies. If you have exclusive shared and ghost, or so you have 3, they are exclusive shared and ghost, and writes to exclusive do not necessitate ghost copies because nothing can be a copy of that. If all of your privileges lack write permission, then FleCSI will actually give you a const pointer or reference when you access the data. But because it's possible to have read-only access to some of it and read-write to the rest, you do have to watch out for the case that you write to a part you promise not to write to. FleCSI will not know what to do with that, and undefined behavior can result. So, and finally, here we have the specific rules for when a ghost copy takes place. They're mostly intuitive, but the thing to point out is the last bullet. If you take out write permissions on ghosts, that means that you are setting them yourself. Maybe you're just clearing values to 0, for instance. And when you do that, FleCSI assumes you have set them to the correct values, and it suppresses the next ghost copy to avoid that communication. If instead you know what the local values are and not the ghost values, then you just do an ordinary write to the owned data, and then a ghost copy will follow. So we've talked about passing things to a task, but the other thing that we have to talk about is how to get data back from a task. A lot of it just is writes to the field, but it's also possible to have tasks return something. So here we have an example of a couple of tasks that return int. When you execute a task, then you get a future that describes the value that it is going to return. But in general, it hasn't executed yet. And so you can call get on the future and learn what that value is, but that means that no other tasks can be launched in the meantime while you're waiting on that one to finish. And that generally is deleterious to performance. So the best idea, which is what's illustrated here, is that you can pass the future to another task and then get the value inside that other task. That way, only that one other task is delayed rather than the machinery that is launching them, and the pipeline can remain full. It's not always possible to do that. Sometimes you do need a task's value to control the logic in the outer program. And in that case, what you should do, if possible, is launch several more tasks before you finally get the value from the future so that the pipeline does not empty entirely. There's one other thing that you can do with futures, which is you can get a reduction to happen. When a task returns a value, you can ask for the values from the different point tasks to be combined into one with the usual operations of sum, product, min, and max, as well as custom operations if you wish. You still get a future back from this, but now the future describes the one reduced result from all of the point tasks. And the same things apply. You want to force that only when you absolutely need it. So, and then I will just mention there is a special case of what's called an MPI task. Because the semantics for task launches are pretty weak, you don't know which processes they're going to run on. You don't know whether they're going to run in order. They might run with multiple copies of the same point task on the same process or not at all on another one. Then sometimes you need stronger semantics than that, especially in order to interface to existing libraries that use MPI. And given that name, we call this an MPI task. So you launch an MPI task, and we stop the operation of, for instance, the Legion backend that's running things in parallel in order to give the floor to that one task and let it do communication. However, these stronger semantics come at a significant cost because this has degraded the entire operation to bulk synchronous rather than having things actually run in parallel. Generally, we use these things to do initialization, to do some sort of communication to establish the initial state, and that's fine. But if absolutely necessary, it can be done later in the process. So we have talked all this time about what it looks like to declare a task. We need to finally say what it means to define one, and the contents of a task are really quite simple. We have a field accessor, and we'll start with a dense accessor because that's the simplest case. The dense accessor can be accessed as an array because it is supplied with pointers to the data. You can use either operator square brackets or the parens to access it. In the latter case, you get bounds checking, so you can opt into that. You can also ask for a span, which is just an iterable view, like the C++20 span, over the data present in the field. Of course, that would include ghosts, so sometimes you might want help from the specialization to identify subsets that are of more interest to iterate over, and we will see an example of that in the next module, in the hands-on and in the next module. If you have one of the more complicated layouts, you have a more complicated accessor. So if you have a ragged accessor, then you can index into it and get one of those rows, which is itself a span, and then you can iterate over that. Or you can iterate over the entire accessor and visit each of the rows in turn, and in this case, we do something with the first element of each of those ragged rows. If you have sparse instead of ragged, it's the same thing except you get a standard map interface instead of a span interface. We talked about mutators. If you use a mutator, you get much the same thing, except that the interface is now bigger because you have the opportunity to change things. Instead of getting a span-like thing when you iterate, you now get each of these now has a standard vector-like interface and supports resizing and inserting and deleting. If it's sparse, you now gain the rest of the map interface, like try and place to create new elements. And if it's a particle mutator, then now it emulates the full standard Hive interface out of C++26, which lets you create and delete particles, as well as simply iterating over the ones that you already have. So, using these things is easy, but declaring them is hard. We will now have an example of how you do that. We will define these tasks. We will restore the whole application to the state where we can run it, and we will visit the different ways that we can define tasks and call them.